1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and so on and so on. This sequence of numbers is what we know as the Pascal's triangle, named by French mathematician Blaise Pascal, but observed by cultures as far-flung as China, Iran, and Mexico. It has many applications in combinatorics, number theory, and algebra, and many, many more. In this video, we'll try to explore some basic properties of the Pascal's triangle through the lens of a bunch of matchsticks. But before we do that, let's note some interesting things about the Pascal's triangle. One thing is its symmetry, with the numbers matching on either side going inwards. Another thing we notice is two numbers next to each other on the Pascal's triangle, sum to the one in the middle. One final thing we'll note is that all of the rows sum to a power of 2. Okay, so now let's set the stage. Let's designate a point A at the top of our board, and let's place two matchsticks in a triangle direction, going left and right from A. Now for every new point, let's do the same thing, not worrying if the matchsticks intersect, and we extend downwards like that, forming a triangle of sorts. Now an interesting question arises. How many ways are there to get from A to this random place I pointed over here? Well, to start off, we can say that we can only go left or right straight downward. Every path we try to draw with these parameters all have one thing in common. They have the same amount of rights and lefts, with there being the same number of steps overall. So we just have to pick when the rights occur in our path. This is where the combination comes in to help us out. A combination is a way to select items from another group of items if order didn't matter, like in committees. We can use the combination to determine the number of ways to get from A to B, choosing the number of rights from the total, and we get our answer, which is 5 choose 3. If we write our combinations to choose the rights specifically, we get this arrangement. We can now organize our triangle into rows and columns based on these numbers, with the rows increasing distance from the top, whilst columns increase the number of rights taken. Now that we've set up a groundwork for our matchstick setup, now let's try and relate the properties that we saw into the picture. So, let's start with the symmetry. We can address this one by noticing that I fixed the combinations based on how many rights I took. So what if, instead, I counted the lefts instead of the rights? Upon doing that, the combinations all flip to the other side. Knowing that these two triangles are equivalent, we can state that the numbers on either side are also equivalent. And that written through the lens of a combination gives us a combinatorial identity. Now, what about the addition observation we saw? Well, let's look at arbitrary point X. There are two other points that can connect to point X. These are called X1 and X2. Those are the only two ways we can get to X. So, the number of ways we should get to point X should be the sum of X1 and X2. Writing these out as combinations and writing X as well as its corresponding combination, we get Pascal's identity, which makes a lot more sense when you're looking at it through the lens of matchsticks. The last observation we saw was the sum of the rows adding to a power of 2. So let's try and calculate the number of ways to get to one row. One thing we saw when relating points to combinations is that every number on one row has the same number on the top. Now we remember that the number on the top states how many steps we would need to take to get to that point, and every point on that row requires the same number of steps. Given that each step has two possibilities, right and left, the number of ways to get to one row is 2 to the power of that row number. So, we can say that the sum of all of the combinations on that row, or with a similar top number, is 2 to the power of that number. Sometimes, when learning a mathematical concept, you never learn the visual understanding of said concept. Now that you've seen that for the Pascal's triangle, I hope you'll do the same for some other mathematical concepts. Besides that, I hope you enjoyed this video and have a very wonderful day.